All right, let's talk problem 4.83. This gives us an equation and asks us to identify the oxidizing and reducing agents in the following equation. To do that, we need to do a couple other things along the way, okay? These things are, again, things that you should learn for this part of the class on oxidation and reduction reactions, or so-called redox reactions. It's really crucial to you, okay? So if we look at the reaction, what's going on? We have some ammonia, 8 copies of ammonia, reacting with 6 copies of nitrogen dioxide to make 7 copies of nitrogen gas, 12 copies of liquid water. Okay? And we're asked about this oxidation reduction reaction. What's the oxidizing reagent? What's the reducing agent? Okay? So to start, we really have to kind of go through a lot of work. Okay? And that work is definitely useful to consider carefully, because what it's going to involve is the assignment of oxidation numbers to individual atoms in the compounds of interest that are undergoing reaction. This is an important skill, okay? Because if you can't assign oxidation states, you're never going to be able to figure out what has been oxidized, what has been reduced, what's the reducing agent, what's the oxidizing agent. You can only guess, honestly, if you can't assign oxidation numbers. And we don't want to guess our problems, we want to make sure we get them right. So let's talk about that. For assigning oxidation numbers in compounds, there are a series of rules that are presented in Chapter 4 of your book. You should know these rules. Crucial. Once you kind of get into them and studying some of them become a little more obvious than others, and it just kind of becomes second nature to you. But you're going to have to kind of invest that time to study them and practice some. Right? Now, when you're assigning oxidation numbers, you look at the compound and you look whether it's charged or neutral. Now, this compound is electrically neutral. And that tells me that when I sum or I add up all of the oxidation numbers for every atom in this compound, I've got to get 0 because it's neutral. Okay? Now, some elements have specific rules written for them, like hydrogen, for instance, has a rule that almost always hydrogen is +1. Sometimes it can be -1 if it's paired up with another metal, but generally speaking, it's +1. So that's the rule I'm going to invoke for assigning the oxidation number to hydrogen. It's +1. Now the thing is I've got 3 of those in this molecule. So that tells me right off the bat that the oxidation number in the nitrogen has to be -3 to offset those +3's. But notice what I did there? When I assign oxidation numbers, I do it on a per atom basis. Per atom basis, okay? But I'm done for that particular compound, okay? I made it work out to get something electrically neutral. Again, I've got this NO2. It's a neutral molecule. When I sum the oxidation numbers of all the atoms involved in the molecule, I've got to get 0. I have 2 elements, nitrogen and oxygen. Fortunately, there's a familiar rule for oxygen. We learned earlier that the charge on oxygen in most compounds is -2. And that is its most common oxidation number, or oxidation state. Sometimes oxygen can take on a different value, like if it's paired up with hydrogen peroxide. But that's a little bit of an exception to the rule. In that case, the hydrogen gets to +1, and because hydrogen peroxide is H2O2 and it's neutral, we have to make this -1. Okay? But it's kind of an exception to the rule. In most compounds of oxygen, oxygen will be -2. And this, nitrogen dioxide, is no exception. So if each oxygen atom is -2, remember, per atom basis, that means that this central nitrogen has to be +4 to make this work, right? If that's +4 and that each one of those is -2, it works out. Got it? All right, moving on. What about the right-hand side? Here, I've got 7 copies of nitrogen gas. One of the other rules to remember, and this one's pretty easy, is that for an element, when it's uncombined with other elements, if it's in its natural state, it just has an oxidation number of 0, just by definition. Okay, so nitrogen has an oxidation number of 0 here. Now what about our last compound? We've got water. 2 elements in water, hydrogen and oxygen. You can really invoke the rule for either one. Hydrogen is usually +1 in its compounds, and oxygen usually -2. I was thinking oxygen, what is 0, right? Usually in its compounds, oxygen is -2. And note that the math works out. You've got 2 H's at +1, 1 oxygen at -2. That works out to being neutral. So I've now successfully assigned oxidation numbers for all of the elements that are in my compounds on a per atom basis. I can start to assess what substance has been oxidized and what substance has been reduced. Before we can do that, though, we have to understand what we mean by these terms. In a reduction, half reaction, what happens is the oxidation number of an element in a compound is lowered as a result of the reaction. It gets lower, a lower number, okay? On the other hand, in oxidation, so lower ox number, okay? Now on the other hand, in an oxidation half reaction, the opposite occurs. The oxidation number increases for an element in a compound as a result of the reaction. So if I look at ammonia, in this particular molecule, the original oxidation number of hydrogen is 1 plus. All hydrogens are 1 plus on the right-hand side, okay? So that hasn't changed. It's not oxidized nor reduced, it's the same. But if I look at my nitrogen, here it was -3, but over on the other side, I turned it into nitrogen gas, which has an oxidation number of 0 by definition. So I went from -3, and the oxidation number increased as a result of this reaction. So that means that ammonia has been oxidized as a result of the chemistry that's occurred. Let's consider the NO2 for a second. Now, the nitrogen in NO2 was originally +4, but after the reaction, now it's 0. That's a reduction because the oxidation number of that nitrogen has decreased. Okay? Or I'll say it's reduced. How about that? Okay? So the NO2 has been reduced. The NH3 has been oxidized. Notice that there's no change for the oxygen. It's -2 both sides. Okay? Now, whenever you have one of these redox reactions, right? Called redox reactions, and they are for a reason. It's a combination of reduction and oxidation. They always come together. So if you've got a complete balanced redox reaction, you got to have something's being oxidized, something's being reduced. This is just the way they work. They always come together as a mixed bag. Okay? So we've identified what's been oxidized, and we've identified what's been reduced. We've assigned oxidation numbers. We've come a long way. But the problem asks us to identify the oxidizing agent and the reducing agent. Now, the oxidizing agent, by definition, is the material or the substance that causes oxidation in something else. So it's actually the material that's been reduced. So NO2 is our oxidizing agent. Likewise, our reducing agent is the chemical that causes reduction in something else, and it in turn is oxidized. So the ammonia is our reducing agent. So it's a little bit confusing, but it makes sense if you really think about it, okay? But nonetheless, what we've shown in this problem is a pretty important skill. You want to be able to assign oxidation numbers, absolutely crucial. You're going to want to be able to figure out what's been oxidized and what has been reduced and explain why that is by virtue of the changes in the oxidation numbers. You're also going to want to be able to figure out what the oxidizing agent and what the reducing agent is. Very easy to ask homework problems or exam problems on this concept, okay? You might see a couple. I mean, it's a very easy question to ask you, okay? So do study this and master the assignment of oxidation numbers based upon the rules that are presented in Chapter 4.